100, but now we'll never know. Okay, so,
You
yeah,
tell
so
we're
today actually,
devastated.
what?
We're devastated, you see.
Okay. So today I won't actually get through 3.6, but we have some stuff to finish up from 3.5. So 3.5 was the non-homogeneous case for our second-order linear differential equations with constant coefficients, and we learned how to choose our particular solution to have the right form. It had to be similar to your g of t, which is the function on this side, but not similar to your homogeneous solution. If it is similar, you can just multiply by t as many times as you need to not make it similar. We did a bunch of examples. Now we're just going to finish off that method by learning how to solve for the arbitrary constants that appear. So let's actually just bring it home with this example. And we're also given 5, 0 equals 1, 5 times 0 equals 0. So now we're going to fully solve this guy. Find all the arbitrary constants that show up in the solution, right? So let's recap what we did so far. How do we start?
Set that equals 0.
Okay, how do we do that?
Set z equals 0.
Set y equal to 0.
Y equals prime.
Right, you pretend this is 0, what do you do?
Characteristic.
Characteristic. He's doing Vincent now.
Oh, that was shots fired.
What, now, how do we solve this? Vincent, you want to continue the roll?
the roots.
How do you get the roots? Come on.
R minus 2 squared.
R minus 2 squared. Yeah, the rest of you have no excuse.
Oh my God, this guy's going at it today.
Well, a repeated roots, right? So, what is our homogeneous solution?
I don't know. I'm just kidding.
T e to the 2t.
Right. Okay, good. So now we are going to want to pick our yp. So remember, what do we want? We want it to look like this, but not. We want it to look like this, but not look like anyone here. So how do we start?
A t squared plus d.
Okay. Any problems?
You gotta multiply.
Yeah, it overlaps with that, right? So we have to multiply by t.
Squared.
And then we realize, oh, it overlaps with that, so you multiply by t again. So that's going to be the general form of our solution. Now comes the part where usually you don't want to leave it in this form. Usually they're going to want you to find the a, b, c, and d. Right? So that's what we're going to do now. How do we get to that? Well, we are going to start by plugging this into our differential equation and then setting the coefficients equal to each other so we can end up finding what these numbers are. So if that's our yp, what does yp prime look like?
2at plus b
2at plus b
plus 2dt e to the
plus
2t
2 dt e to the 2t plus
dt squared e to the 2t.
plus what?
Dt squared e to the no 2
Two, yeah.
Okay. Now at this point, I'd simplify in each step if it can be simplified. So like here, I can sort of make it look a little bit nicer by just factoring out the e to the 2t, or 2e to the 2t. And d t. It's probably better to do this. dt plus dt squared.
Can't you also factor out the d?
Yeah, the d would be nice. I don't want to factor out the t because they have to do like this triple product rule thing. So let's factor out 2d. And make a difference. So now I only have to do the product rule once instead of twice before. So now I go to the next step. What's the second derivative?
2a plus 2 de to the 2t.
No,
Plus, no?
That's
plus 2 e to the 2t times 2.
There's a d here.
I said
So-
2d equal to
Oh,
t.
4.
4d e to the 2t times t plus t squared plus, now I leave this part,
You said the 2 twice.
2d e to the 2t, and I differentiate inside here, 1 plus 2t. Okay? So now plug into ODE. So we're going to plug this guy in. So what are we going to have? We're going to have 2a plus 4d e to the 2t minus 4 times this guy. So we're going to have 8at plus 4b plus 8d e to the 2t t plus t squared plus 4 times our original y, 4at squared plus 4bt plus 4c plus 4dt squared dt. And all of that is equal to t squared plus 12e to the 2t. Now, how do you think we proceed from here?
Wait,
What is
Professor,
this?
What about the homogeneous?
Simply substituted yp prime and yp double prime, right? Shouldn't there be a minus 4 to the second one?
I did do it. I already multiplied
Oh,
it.
you already did, okay.
These were 2s and 2s. I made them 8s and 4s.
Oh,
I already did the
okay.
multiplication.
You should cancel terms.
You sort of equate like powers of t. So you're going to sort of regroup these terms, right, into all the like powers. So let's start with quadratic terms, or it doesn't really matter what you start with. Eventually we want to get to just a nice compact form where we group all the like terms. So how do we get to that? Start.
2a plus.
Wait, first choose who you want to group first. Who do you want to deal with first? All the t squared terms or all the exponentials? Right?
T squared.
Okay, let's deal with all the t squares. How many t squares do we have on the left side? Right? There's no t squared here. There's no t squared here. T squared
What about
here.
that one?
Then the
T plus t.
There's none here. There's only one here, right?
What about the one in
The
parentheses?
parentheses
line,
on the
second
first
third.
line.
It's a t squared e to the 2t.
But about
Oh,
t
okay.
plus
But it's-
t squared.
It's, like I said, when you multiply out, it's not a t squared. It's a t squared times e to the
Oh,
2t.
oh.
I only want t squares, right? There's none here, there's none here, there's none here, there's none in here. There's only one here.
And 4.
So we have 4a t squares. What about the t's? How many t's do we have? None here, none here, none here. Here, we have a t, right? So we have minus 8a. What else do we have with t's? Here, right?
4b.
Plus 4b. And I think that's it. How many constants do we have? Things that have no functions attached to them. Well, we have a 2a,
4b. 4b.
nothing
B
here,
and 4c.
minus
And 4c.
4d,
Plus, yeah, minus.
right? Because the negative sign out here. What else? Plus
4c.
4c,
Yeah, that's it.
and that's it. Plus. So that deals with our quadratic. Now let's start with our exponentials. Let's look at the guys that are e to the 2t. Now remember, that's different from t e to the 2t and t squared e to the 2t. Guys that with only e to the 2t times a constant, right? None here, none here,
2d
Not there.
here. right? We have 2d. None here, none here. That's it. Plus, now let's look at the TE to the 2t's. Where all our TE to the 2t's. Here, we have 4d.
Another 4D.
We have another 4d from this one when we multiply out.
8D.
Minus 8d.
4D.
Where do you see 4d?
Oh no,
This is
that's
a
T
T
squared.
Okay, plus...
Would it make sense to get rid of that because it comes out to 0?
Yeah, it comes out to 0. We're going to ignore it, essentially. Now, let's look at our t squares e to the 2t's. How many of those guys do we have?
4D.
4d.
8D.
This is on... No, that doesn't
No.
work.
8D.
Here, we have minus 8d. Don't forget that sign. What else do we
And then
have?
4D.
Plus 4d.
Oh, okay. And also 0.
And that's also 0. So these two guys you can essentially ignore. Now, remember, this is equal to t squared plus 12e to the 2t. So what does that mean for us? Now we do this whole equating coefficients maneuver, something that you've seen before in Calc 2, of course. So now we sort of match up both sides. I have 1t squared over this side. Over here I have 4at squared. In order for them to be equal, I have to have the same number of t squares on both sides. This implies that 4a must be equal to 1. That's the first equation. What else do I have? I have 0 t's over here. So one thing you're going to have to do is imagine that there are things here with 0 coefficients, right? There are no t's over here. Over here, this is the amount of t's I have. That would also mean that minus 8a plus 4b must be equal to 0. That is the second equation I have no constants on this side, which means this, the constant term, has to also be 0. 2a minus 4b plus 4c equals 0. That's the third equation I have. How many e's do I have on this side? E to the 2t's? I have 12 of them. On this side, I have 2d of them, which means 2d must be equal to 12. And these guys don't even come into the picture, right? And so now we need to solve for all these guys. What do we have? Well, we know that a is equal to 1 over 4 from equation 1.
And D is equal to 6.
From 2, you can get, oh, we also know that d equals 6. From 2, I can plug in the a here, right? And what does that mean b?
Minus a half. Or am I doing it upside down?
No, it's going to be 2 divided by 4, so it's going to be B is equal to a half. Positive a half.
Positive half, right? Because you'd move it over and then...
Oh, okay.
Right, so now, so we have A, B, D. The only person missing is C, so we can just plug that in. We have, from 3, we have 2 times A, which is a quarter, minus 4 times B, which is a half, plus 4 times C gives us 0. So this is a half minus 2 plus 4c equals 0. This means that c is equal to 3/8.
Yeah.
So let's plug these guys in. So our particular solution will be 1/4 t squared plus 1/2 t. C is 3/8. plus 3/8. D is 6 plus 6 t squared e to the 2t. So this is a specific function, a very specific function that solves the original ODE. Right? If we plug it into the original, it will actually work. Now, our y must then be equal to c1 e to the 2t plus c2t e to the 2t plus 1 over 4t squared plus 1/2 t plus 3/8 plus 6t squared e to the 2t. Any questions so far? Yeah, but wait, so far, is everyone following? Just want to make sure I'm not losing anyone.
Not yet.
So, okay, so just to recap quickly before we move on further, because now we've actually found specifically YP. You had this general form, which we knew how to choose since last time. You wanted it to look like the G of t, but not like the YH. So we ended up with this. Now the question is, what are these arbitrary constants, right? So now what do is we find the derivatives, we plug it into the original differential equation, and we got to this equation. Then we simplified, we grouped all the like terms. So we grouped all the t squares and all the t's and all the constants, all the e to the 2t's, all the t to the 2t's, all the t squared e to the 2t's, and then we equated coefficients. The number of things over here must be equal to the same number of things over there. So the amount of t squared on this side is the amount of t squared on that side, and etc. You just equate the coefficients, you get this system of equations, which hopefully you know how to solve, and then we finally get here. Are we good? Okay. So now, we were given initial conditions, which means these guys, they also expect us to find.
That's a lot.
Which is just like before, right? So how did we actually do that before?
We go to.
We're going to need the derivative again as well. So y prime is going to be equal to 2c1 e to the 2t plus c2 e to the 2t plus 2c2 t e to the 2t plus
My God.
1/2 t plus 1/2 plus 12t e to the 2t plus 12t squared e to the 2t.
Hey, why do you do that just in the homogeneous solution instead of making all that?
What do you mean?
Like just taking derivative of the homogeneous solution and then plugging the initial values. Why do we have to do it the whole thing?
Because the homogeneous solution isn't the general solution. When they give you the initial conditions, what did they say here, by the way? Y of 0 was 1, and y prime of 0 was 0. Right. When they say y here, they're talking about the general solution, right? So it's not good enough to just have the homogeneous one, right? So whenever you're trying to find the initial condition, you have to plug in the general solution, right? So then y of 0 is equal to 1, which is equal to, you just plug in 0 for t's in this equation. It won't end up being that bad, because the t equals 0 is going to kill a lot of people. Like, this is not going to be there, this won't be there, this won't be there, this will be there, and that won't be there. And since y prime of 0 is equal to 0, that's equal to, now I plug in 0 in this equation. So that's 2c1 plus c2, 0, 0, plus 1/2, 0, 0. And so we have that. And so from here, we have that c1 is equal to what? c1 is equal to 5/8, which means that I can plug in 5/8 over here, and I get 5, and I get 0 is equal to 5 over 4 plus c2 plus 1/2, which means our c2 is what? Huh? And finally, we have the general solution. C1 is 5/8. C2 is minus 14/8. Yeah, and then the rest of it we just copy down. T squared plus 1/2 t plus 3/8 plus 6 t squared into 2t.
Wow. I like how you write finally.
Finally, yeah.
Would have
Oh, yeah,
been
the
on
problems
the
get
test.
long eventually. Yeah, I know it's a crazy example to give, but it's actually a final problem.
My God.
We're actually expected to do this on a final. I forgot which one it was. I didn't write it down, but it's on a past final. When you're going over your review, you'll see it at some point.
Did you post a review yet?
No. I'll do it today.
So if the particular solution is two functions, it's going to be
Where's your review?
It's on his website.
If it's like, let's say,
Yeah, this process is a general process. Your functions might be
It's in
different,
the
but you'll
syllabus.
essentially do the same thing, no matter what. So you guess what the solution looks like. You find all the derivatives, the particular solution, find all the derivatives, plug it into the original. Then you equate coefficients to find what those variables are. Then you're going to plug it into the general solution, and then if you're given initial conditions, you have to differentiate that and plug in your initial conditions. So, some comments. Note that you're not always required to take it this far, so I just should mention that because I've seen this all the time. Sometimes I'd say, don't solve for any arbitrary constants, and people still going through all this. So I just want you to know.
Extra credit.
No, you don't get extra credit. In fact, I'm more inclined to deduct points, especially if you get this wrong, I'm going to be so mean. Okay. Follow instructions, right? So you're not always required to go the whole way. You're not. Right? So sometimes the question will say, you don't need to find any of the arbitrary constants. In that case, don't. We could have stopped when we were right here and we had those A, B, C's, and D's. You could just stop there, right? That's if they say, don't find any arbitrary constant. Just stop there, right? And if they don't say that, then you'd have to take it to that is not said.
All the way.
No, take it to equation, let's number this one. Call that, well, technically I've been numbered. Call that equation 5. Take it to equation 5 and stop. If initial conditions are given, then you go as far as equation 6. So like I say, the problems are long and tedious. Sometimes they might not require you to do everything. Just pay attention to what they're saying. Right? So there could be a case where you have to leave in the C1, C2s, the A, B, C's, and D's. That's fine. They'll tell you, don't bother solving for the arbitrary constants. If they don't say that, then they always expect you to get to a specific YP. So they're going to, you're going to need to get to equation 5 And if you're given initial conditions, then you have to go further and solve for the C1 and C2. So hopefully conceptually that wasn't difficult to understand, but as you can see, it's long and the algebra can get to you if you're not careful. Any questions? Did you get the numberings, Nettie?
Yes.
All this 5? Okay, good. All right. That's it basically. I want to go to 3.6. 2.6 talks about variation of parameters. It's basically another method to get to the YP, right? So turns out it's not always as easy as the undetermined coefficients method. And I'm going to show you why in a bit. I'm going to call undetermined coefficients UC. One, undetermined coefficient works only if we have constant coefficients. So if you end up with a differential equation that doesn't have constant coefficients, you are out of luck. Undetermined coefficients relies on the fact that we can make things similar, right? Well, things aren't similar anymore if you're multiplying by variable functions. Another thing is undetermined coefficients works only if g of t is similar to its derivatives. So notice what happened in undetermined coefficients. I pretended something looked like g, and I did all this derivatives, but there came a point where I had to sort of match up both sides, right? It turns out if I took the derivatives and the functions looked completely different, then matching up both sides wouldn't really work out to our advantage, right? Because the function would be completely different on this side compared to on the right side, right? So if you start taking y prime and y double prime and all that sort of stuff, and the functions look completely different from what the original g looked like, it doesn't really work, right? So the reason why undetermined coefficients work with polynomials, exponentials, sines, and cosines is because the derivative of a polynomial is a polynomial. The derivative of sine and cosine is sine and cosine. The derivative of an exponential is an exponential, right? That's sort of why it works out. So when we're taking derivatives, we could match up both sides and it wouldn't be a problem. There are cases though where this doesn't work. So for example, UC cannot be used. To solve something as simple looking as that guy. And if you start to think about it, you will realize why. If you're given this differential equation, you can't really use undetermined coefficients because it's going to be hard to predict what the particular solution looks like. Because what's the derivative of tangent? What's the derivative of tangent? Secant squared. And what's the derivative of that?
What?
Secant.
See, I'm not the only one that doesn't know.
Yes, 2 secant squared tangent x, right? And if you take the derivative of that, it gets worse. You have to use the product rule. You get 2 terms. Turns out that every time I take the derivative of tangent, I get something that looks completely different, right? Tangent actually has an infinite number of linear independent derivatives. There is no general formula I can say, oh, the particular solution should look like this. There's an infinite number of things to choose from, right? It just wouldn't work. I cannot pick functions that would look like, its derivative would look like. So now the question is, how do we actually get to a solution then? Right? Turns out we can use a method called variation of parameters to get to someone like this. So right, if your right side is not a polynomial or an exponential or sine and cosine or a polynomial times any of those or an exponential times any of those, we can't predict what the derivatives would look like, and so we need something else. We need something a bit more general. Right? And that is called variation of parameters. So what did I say here? So I'm going to actually develop the method. So remember in reduction of order where we sort of generalized our solution, what it looks like? We know if we had a first solution, we assumed that the second solution was a function times the first one. We're sort of going to do that here, right? So this is why it's called variation of parameters. Your parameters here can now vary. We don't assume they're constant, right? Where y1, y2 are fundamental solutions to the homogeneous case. Now, a priori, we don't know the solution would look like this, but it's something we tried and it seemed to work out. Yes?
What is the word after hour?
Q.
Q.
That looks like a T, but it's just.
Yeah, it's like a cliche. Take your cue from yeah, so we assume that we can vary the coefficients of your homogeneous solutions and somehow get a particular solution. That's sort of what we're assuming here. Beforehand, we don't really know that this is the case, but it's something we tried before and it seemed to work out, so we're going to try it again. And so let's run with this, right? This would mean that yp prime would look like what? Yp prime would look like? U1 prime y1 plus
U2 plus
y1 prime plus u2 prime y2 plus u2 y2 prime, right? So just product rule, okay? So we can actually, now here's one thing that we're going to do. This we can write as u1 prime y1 plus u2 prime y2 plus u1 y1 prime plus u2 y2 prime. This guy, as the method goes, we're going to assume this is equal to 0. Now the question is, why can we do that? Why is it okay? Why would we want to do that? Well, one, we know it's okay because remember, as in 3.5 we learned, it doesn't matter which particular solution we get, any one would work, right? So I want to pick one where this is the case, where this operation actually works. Why would I want that particular operation to actually work? Well, my goal would be to solve for u1 and u2. So I don't really want the derivatives to get too large, right? If I leave in the y1 prime, and the next step is going to be a double prime. And the next step would be a third prime. I'd get a whole set of differential equations to solve for the u. I don't want this to happen. So at every stage, if I get a higher derivative of u, I'm going to assume that part is equal to 0, right? And it's okay in theory because it doesn't really matter which yp I find. I'm going to try to find the easiest one, right? As long as we make an assumption that doesn't get us in trouble later, it's okay. And this actually doesn't get us in trouble, right? And moreover, this gives a condition. u1 prime y1 plus u2 prime y2 should be equal to 0. Now let's call that equation, that's equation 1 in this section. So we have that condition. Now let's go further. What would yp double prime look like? Now remember, yp prime is just this part. So yp double prime would be
u1
prime, y1 prime, plus u1 y1 double prime, plus u2 prime, y2 prime, plus u2 y2 double prime. Now we're going to plug this into our general form. Y double prime plus p of y plus qy equals g. Remember, this is our general form that I'm using. This means what would we get? I would get u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime plus p times that guy, u1 y1 prime plus u2 y2 prime plus q times our original assumption, u1 y1 plus u2 y2, and this should be equal to g. So what would we end up with? Well, it turns out we'd end up with u1 times y1 double prime plus p y1 prime plus q y1 plus u2 times y2 double prime plus p y2 prime plus q y2 plus what we would be left with so what do we get rid of? We got rid of this term. We got rid of this term. We got rid of these terms. So all we're left with is u1 prime y1 prime plus u2 prime y2 prime equals g. Don't worry, we'll see the light at the end of the tunnel soon, don't worry. Here's the thing. What can you tell me about this? Yes?
Professor, how to get the YP double prime?
Differentiate this. Right?
What about the upper
Yp prime was this. This equals this, and I assume this part was 0, so it's only that. I differentiate that to get the second derivative. Plug that into my differential equation, I end up with this thing.
That's the general form of a differential equation, a non-homogeneous.
Yes, but what is y1? What do we assume y1 was?
0.
It has to be 0. Why? Because I assumed y1 and y2 are fundamental solutions to the homogeneous case. Which means when I plug into my differential equation, I get 0. The same thing will happen here. This will also give me 0. So I end up with just this equals g. Now let's call that my second equation.
Which one was the first?
This one here was the first. The equation I got as a result from making this assumption was my first equation. My second equation is this one that I got by plugging into the stuff. This gives us a system of equations. u1 prime y1 plus u2 prime y2 is 0, and u1 prime y1 prime plus u2 prime y2 prime equals g. So the system of equations. Now, I want to solve the system using Cramer's rule. You don't have to use Cramer's rule, but using Cramer's rule is going to allow us to write down a formula in a very nice form, so I'm going to use Cramer's rule. So, by Cramer's rule, what do we need for Cramer's rule? Now remember, what I want to find is u1 and u2. So I'm thinking of u1 prime as my variable and u2 prime as my variable, right? So my y1 and y2 are like the constant terms here. So the d in Cramer's rule would actually be what?
Boom.
What? y1?
And y1 prime, y2, and y2 prime.
The determinant of that. But what's that determinant?
y1, y2 prime minus.
What is it in definition for something? You should be familiar. It's the Wronskian. This is the Wronskian of y1 and y2. Let's call that w. Now, the next thing we're going to need to find is to find the d for u1 prime, which is going to be, I replace the answers column with the first column. So instead of y1, y2, I put 0 in g. This stays y2, y2 prime. I'm going to call this w1. The u2 prime is going to be very similar. I'm going to replace the answer column with the right column. I'm going to call that w2. Yes?
How are those two parts 0?
Oh, right here.
Yeah.
Because in the beginning I assumed y1 was a solution to the homogeneous equation, which means if I plug it in here, I should get 0. Remember, homogeneous is when you have 0 on this side. y1 is a solution to that equation. So if I plug it in here, I should get 0 as the result.
But then why is the second part 0?
Same thing, y2 is also a solution to the homogeneous equation. I assumed that before I found the two homogeneous solutions, I called them y1 and y2, which means when I plug them into my differential equation, I get 0. Okay? So eventually we end up with that system, which I'm solving by Cramer's rule. These are the determinants that I need. Right? This one I call w, which is the d. It's the Wronskian. To find the solution for y1, u1 prime, that's w1 and w2. Now notice that here, this is actually equal to what specifically? How do you find the determinant of this?
Negative y2g over
Negative y2g. Now what is this one?
y1g.
y1g. Right? We'll get back to that soon. But for now, just think of this as w, w1, w2. Okay? So now what do I have? So by Cramer's rule, what is the solution for u1?
negative y2g.
Tell me in terms of w's, because I want this one.
w1 over w.
w1 divided by w. This would mean that u1 must be equal to what? So the antiderivative of that. Similarly, u2 prime is equal to w2 over w, which means that u2 is actually the antiderivative of that. This means since my yp I'm taking to be u1 y1 plus u2 y2, my yp would be equal to y1 times the integral of w1 over w plus y2 times the integral of w2 over w. Or, more specifically here, my particular solution, according to this method, for the second order homogeneous second order non-homogeneous differential equation is going to be y minus y1 times gy2 over w, because that's what this was, plus y2 times integral of gy1 over w. And that's actually what our particular solution would look like. Now, this is a general method, which means as long as these integrals are doable, it will give us a particular solution. So we get 0.6.1. It says given y double prime plus py prime plus qy equals g, with P, Q, G continuous on some open interval I. And Y1, Y2 are fundamental solutions. Then, our particular solution will always be given by minus y1 times integral of g times y2 over the Wronskian dt. Technically, you make this a definite integral because you want it to end up with a function anyway. 2 t0 to t gy1 over w. According to variation of parameters, you will always have a general solution that looks like this form. And it will work as long as those integrals are doable, or if it's okay to leave your answer in terms of integrals, that's what your solution will look like. This is called variation of parameters. Now the derivation is scary, but we're not going to ask you to derive it. I'm just showing you. You just have to pretty much memorize this. Which it's not as bad as you think. No, we've been through the worst. The derivation is the worst thing. Basically, yp would look like y1 times integral of w1 over w plus y2 times integral of w2 over w, where w is the Wronskian of y1 and y2. w1 is the Wronskian with first column replaced by 0g. w2 is the Wronskian with second column replaced by 0g. And I like to remember it this way because it actually works in general, which means if we had a third or a fourth order, we could have y1 times w1 over w, y2 times w2 over w, w3 over w, w4 over w, up to wn over w. This will actually work in general for higher order differential equations. So, but basically that's it, and if you really flesh out what w1 and w2 are, you get the formula that I have over there. But I guess when we get to chapter 4, I'll talk about the general case. But that is basically it. Let's actually do some examples so we can stop being confused and see this in action. Let's go back to that first guy that I mentioned. Y double prime plus y equals tangent. I need to make sure all my functions are continuous, so let's do this for t between 0 and pi over 2. How do we start? Well, we need to know what y1 and y2 are, so the first thing we do is find those. How do we find y1 and y2? Homogeneous solution. Get r squared plus 1 equals 0. This means r equals plus or minus I, which means our homogeneous solution is c1 cosine t plus c2 sine t. Let me call this guy y1, call that guy y2. Which means my particular solution would look like minus y1 times the integral of g times y2. Well, we have to find one. The next thing we have to do is find the Wronskian, because we're going to need it in the formula. Wronskian is cosine, derivative of that is minus sine, this one is sine, derivative of that is cosine. Cosine squared plus sine squared, you actually get 1, so that one's actually nice. Now we can go. This implies yp is equal to minus y1 times the integral of g times y2 over the Wronskian plus y2 times the integral of g times y1 over the Wronskian. And so this is minus cosine t times, this is tangent times sine t dt plus sine times, tangent times cosine is what? It's sine. All right, how do I integrate this? Quickly, we don't have a lot of time. Break up tangent in 2, sine over cosine, then we would get sine squared over cosine. How do you deal with that?
The Langle formula.
Break it into 1 minus cosine squared, then you divide cosine into each. Eventually you will end up with secant t minus cosine t plus sine t times 0 sine t dt. Okay? And now we have minus cosine t. What is the integral of secant? ln of plus tangent t minus integral of cosine is sine plus sine times integral of sine, negative cosine, so this is negative cosine. Now negative cosine times negative sine gives you positive sine cosine, which is going to kill this. So these terms are going to die, and we are going to end up with minus cosine t ln of secant t plus tangent t. Now, given this, who would have guessed that the particular solution has this form? But then we're done. the general solution is C1 cosine t plus C2 sine t minus cosine t times ln of secant t plus tangent t. Yes.
What about the constants of the equation?
Right. Remember the formula that I wrote down? Technically, there were definite integrals. The arbitrary constants died. T naught you pick to be a convenient point that will kill all your plus c's at the end. Right? And you can prove that you can always do this, but it's not important for us to know that why that works. Because again, remember, it's any YP would work. So you pick the one that's nicest. Right? But that's basically it. So you're given a random differential equation. This side you realize it doesn't fit nicely with undetermined coefficients. That's important to note because usually they won't tell you. They won't tell you, oh, use variation of parameters. They're just going to give you a differential equation. You should know if you can use variation of parameters or use undetermined coefficients. Here though, tangent, you realize it doesn't look like any of its derivatives, so undetermined coefficient will not work. So you know you have to do variation of parameters. Find the homogeneous solution, call one y1 and y2, pick who's who. Then you have to find the Wronskian of those two. In this case, it was 1. Then you have that formula. It's minus y1 times g times y2 over the Wronskian, plus y2 times g times y1 over the Wronskian, right? Which the formula you would have memorized at this point. At this point, you'd have this memorized, like you know that. Then you just go through and you have to just do the integrals, right? As long as they're nice enough to evaluate, which in this class they will always be, you can evaluate them. That gives you the particular solution. And so now the general solution is just the homogeneous plus the particular. Let's do it again. Another example. Y double prime plus 4y prime plus 4y equals t to the minus 2e to the minus 2t. Here I'm setting t to be greater than 0 to make sure all my functions are continuous. Notice that this cannot work with undetermined coefficients because it won't look similar to any of its derivatives. The power will always get higher in the denominator, which makes it an unlike term. All your derivatives would be unlike terms. Right? So undetermined coefficients does not work because this is not a polynomial. Right? So now we try to use variation of parameters. The first thing we need is to find the homogeneous solution. This means that r plus 2 squared equals 0. So r equals minus 2. It's a repeated root. This means your homogeneous solution is C1 e to the minus 2t plus C2t e to the minus 2t. We're going to call this y1. We're going to call that y2. After we find the homogeneous solutions, we're going to need to find the Wronskian. So now I'm going to find the Wronskian. E to the minus 2t. The derivative of that is minus 2 e to the minus 2t. T e to the minus 2t. The derivative of that would be e to the minus 2t minus 2t e to the minus 2t. This times that, I would get e to the minus 4t minus 2t e to the minus 4t. Minus this times that, which becomes a plus 2t e to the minus 4t. This will die, so this is just e to the minus 4t is my Wronskian. This means the particular solution is minus y1 times the integral of y2 times g, which was t to the minus 2 e to the minus 2t, all over this was actually 2. All over the Wronskian, which is e to the minus 4t, plus y2 times integral of y1 times g all over the Wronskian. This simplifies here, this kills those here.
Y1 is
We have-
e to negative 2t, right? Not 4t.
Yeah,
No, that. The other left side.
oh, this, yes, negative 2. Got used to the negative 4. So this gives us t times t to the minus 2, which is t to the minus 1. We integrate that, we would just get ln, right? So it's minus e to this times ln of t plus, this is just t to the minus 2. The antiderivative is minus t to the minus 1. Which the t's would cancel. And so here it gives my particular solution as this part here, though, reject y. It's redundant. It's a part of the homogeneous solution. It's a homogeneous solution. Right? That happens sometimes. Just ignore that part. And so now we can have the general solution. C1 e to the minus 2t plus C2 t e to the minus 2t minus e to the minus 2t ln of t. T is greater than 0. Technically, I don't need the absolute values here, but I rather err on the side of caution. It's still technically correct. But if you didn't have the absolute values here, it's still fine. But that's it. Let's do it again. Step 1 is
No, homogeneous.
find the homogeneous. R squared plus 9 equals 0. This means R is equal to plus or minus 3i. This means the homogeneous is C1 cosine 3t plus C2 sine 3t. Done. Second step. Wronskian. Right, so this is the first step. Second step, Wronskian.
Cosine 3.
Cosine 3t. This is minus 3 sine 3t. Sine 3t. 3 cosine 3t. That would give us 3 cosine squared plus 3 sine squared. That's just 3. Then the third step. Find the yp. Remember, it's going to be, no, the first few times you're doing this, I'd recommend you write down the formula every time. Times g times y2 over w. I mean, I didn't do it the last few times, but if you're learning this for the first time, I recommend that you always write down the formula. Then you just plug in y1, I'm going to call this the cosine. y2, I'm going to call that the sine. So it's minus cosine 3t times the integral of g secant 3t times y2 sine 3t all over 3, well, 2 secant. Remember, technically it's a definite integral. We're going to ignore the constants. y2 sine 3t, integral of 2 secant 3t times cosine 3t over 3. What does this simplify to? Minus 2/3 cosine 3t times the integral of secant 3t times sine 3t is what?
Oh, tangent.
It's tangent 3t. Plus here I have 2/3 times sine 3t. Integral of secant 3t times cosine.
That's just. Oh, it's 1.
It's just 1. So our yp is minus 2/3 cosine 3t. What's the integral of tangent? What's the integral of tangent? Negative ln of cosine. And we do a substitution, so that becomes 2/9 plus integral of 1 is just t, so this is just 2/3 t sine 3t. This means your general solution is c1 cosine 3t plus c2 sine 3t plus 2/9 cosine 3t cosine 3t plus 2/3 t sine. That was the last example. Now, just to bring it home, the things I said about form and algorithm, if I were you guys, this is sort of how I'd approach the situation. I never really wrote this down. I'm going to write it down now, but in general, even if I don't write this down, this is sort of how, when you read over your notes, this is what you, the kind of notes you should be adding. So you should have something called variation of parameters. Of course, you're going to know all the forms and all that. That's going to be important, but you need to know how to do it. Well, the first step is to check if you see will work. If not, step 2 is to find the homogeneous solution. Find the Wronski. Step 4, find yp, where yp is equal to minus y1 integral of gy2 over w plus y2 integral of gy1 over w. Plug in. Your general solution would be c1 y1 plus c2 y2 plus your yp. So this is the algorithm for variation of parameters, right? So when you're reading over your notes, or you want to put something on a flashcard, this is what you'd write on a flashcard. This is what you should know as good as you know your own name, right? You just know variation of parameters. What do I do? Check if this works, find the homogeneous, find the Wronskian, plug into this formula, done, right? You should have those steps in your head, right? So when you go in a test and you're freaking out, oh, what do I do next? You know, your prime directive takes over. Okay, next step is blah, right? Like the Terminator, right? You see that list of objectives over here, right? When things are blowing up all around you, you're like, okay, next objective. This should be burned into your brain, right? Right. This is how you like don't freeze on tests and like I couldn't write anything, I don't remember anything. If you know this, you'll never like freeze. Well, unless you forget how to integrate, then that's another problem. That's something you deal with separately.
Are you hinting at the fact that we're going to have a question quoting Terminator on our exam?
No, not particularly.
He's a fan of Terminator.
All right, we're done.